Hi everyone, my name's Nicholas Belston. I'm a graduate researcher with the MIT STAR Lab, the Space Telecommunications, Astronomy, and Radiation Laboratory. And today I'm going to be talking about a open source, flexible, electronic and graphical user interface system to control Helmholtz cages. Helmholtz cages are used to test magnetometers and spacecraft magnetic attitude control systems. And it's pretty common for universities to build their own Helmholtz cages from scratch. There are commercial options available, but they're expensive, and there's some value to the learning experience of building your own test equipment from scratch. So there have been a number of ways that university teams have used large amplifiers to create controlled magnetic fields through Helmholtz coils. Some typical versions involve using a programmable power supply with a polarity control switch or a fairly expensive 4-quadrant power supply. But today we're going to talk about a very inexpensive option, which is to use a DC coupled audio amplifier. A lot of modern amplifiers are AC coupled, so those won't work for this application. But in this case, we're using the Crown DC 300 Series 2 amplifier, which only costs about $300 per unit, and it can control 2 axes. So we have a per axis cost of only about $200. And these can drive quite large coils. Our target Helmholtz cage system is the MIT Space Systems Lab 4-coil Merit Helmholtz cage. This is about 1.5 meters per side and requires about 5 amps at 18 volts in order to achieve the full control authority. And these amplifiers are plenty powerful to drive those coils at those levels. And what we've created, and what I'm reporting on in this poster presentation for the CubeSat Developers workshop, is a electronic and GUI control system that works with these amplifiers to create a fairly user-friendly Helmholtz cage. We've created a modular architecture to serve each of the electronic needs of a Helmholtz cage control system. So at the lowest level, we have what I call the controller root, which is just a microcontroller. It's a Teensy 4.0 microcontroller, which is compatible with the whole Arduino development environment, so it's pretty easy for people to get started and to modify the code on their own. That's integrated on a little custom board with a bidirectional power supply. And on that board, you could stack a bunch of nodes. There are sensor nodes and driver nodes. Each sensor node is manufactured the exact same, so you don't have to buy several boards for each axis. A little solder bridge just sets which axis it listens to. And For the Space Systems Lab Helmholtz cage that I've been designing for, we've chosen to use 2 sensors and 3 drivers, and you can see in the poster a picture of that stack. But there's no reason to stop there. As implemented, I think that we can support up to 6 sensors and 7 drivers, so you can imagine like a pair of nested 2-axis or 3-axis Helmholtz cages, and this system could drive it. And you can place sensors around your test equipment and get live magnetic field feedback, all with this electronic system, just with some changes to the microcontroller hardware and the control hardware running on a PC. So this is very flexible based on your testing needs and also what equipment you have available. We've used these large Crown amplifiers, but this will work with any audio amplifier. The driver nodes close the feedback loop around the current flowing through the coil. So you just have to provide a audio amplifier with sufficient power for your coils, and the control system will make sure that you receive the current that you ask for out of these DC coupled audio amplifiers. The way we do that is discussed in the driver implementation section of the poster. The microcontroller communicates with a digital to analog converter on each driver node that creates a reference voltage. That feeds into the positive input of a feedback amplifier that works with a current sense amplifier attached to the negative input. That closes the feedback loop with negative feedback, and therefore, no matter what the gain of the audio amplifier within reason, you'll get the current requested from the digital to analog converter. And all of the conversions from currents to counts based on all of the analog electronics are taken care of inside the microcontroller. Then we have a 30 hertz low pass filter, and this sets a dominant pole so that the entire closed loop system is stable. Otherwise, you could get oscillations. And then finally, there's a little op amp serving as an output amplifier that's limited to the input range expected by the audio amplifier, which is about plus or minus 1.2 volts. Therefore, you're not going to damage your audio amplifier even if something about the electronics is wrong. Each sensor node it actually communicates with a remote sensor over an Ethernet cable. We've used the PNI RM3100 sensor. It's only about $60 in an integrated package and is quite accurate. It has a sensitivity of 26 nanotesla and a measurement range of plus or minus 1100 microtesla, so plenty for any ADCS control systems. And we communicate that with a remote SPI chip, the LT6820, so that just needs a single twisted pair to communicate the entire SPI protocol. So we use one twisted pair of the standard RJ45 terminated Ethernet cable for the single twisted pair SPI, and we use another twisted pair to provide power. Since the RM3100 uses so little power, we can actually power the whole thing over an Ethernet cable, even out to cables of 20 or 30 meters long. The microcontroller, so then at a low level, you could send current commands to the microcontroller and receive back B field response, but that isn't very user-friendly. So to take it another level, we've created a GUI control system, which is implemented in MATLAB. So that just takes over the serial port of a standard PC and communicates with the TNC 4.0 microcontroller, and displays all the information in a more user-friendly way than just kind of typing over a serial port. So in our GUI, I'd suggest everybody go to the CDW website to go look at the actual picture. But in our GUI, we have the capability to connect with the microcontroller. Then you could set offset values in microtesla and gain values in microtesla. That corresponds to the gain in microtesla per amp, and that way the same control system can be used for many different Helmholtz cages without adjusting the software. All you have to do is type in new values. There are sliders to request a current manually, so you could say x-axis 50 microtesla, and the control system will change the current flowing through the coils accordingly. There is some live feedback provided of the magnetic fields at each sensor node and the currents flowing through each coil. And there's a few noise monitors and time step monitors to make sure that the entire software, electronic, and hardware system is operating as you expect. And finally, there's a live, continuously updating B field plot that allows you to see the magnetic field in the 3 axes change over time. So that's really useful if you're running a job from a job file, which is another capability. You could see how the commanded magnetic field has changed over time and make sure that everything is actually responding the way that you expect. So our control system will work with many DC-coupled audio amplifiers and will provide current control to implement a Helmholtz cage. As a proof of concept, we've retrofitted this control system to the MIT Space Systems Lab Helmholtz cage, which is about 1.5 meters per side. But all of the hardware can support a wide range of Helmholtz cage designs and sizes, as long as the audio amplifier supplied can provide the necessary voltage and power. And all software and design files, including the Gerbers necessary for each of these boards, have been provided on my personal GitHub so that it's publicly available to everyone. If you want to look at it, again, look at the poster presentation on the CDW website for 2021, and you'll find the link. And I encourage everybody who is interested in creating their own Helmholtz cage, feel free to use all of the files there. You could take those Gerbers and upload them to your favorite PCB manufacturer like Oshpark or something like that, and order them for yourself. It'll probably only cost $300 or $400 for all of the boards manufacturing and components from your typical supplier like DigiKey. And I also encourage any user interested in using or contributing to this project to contact me at my email, which is also available on the CDW website. In the future, myself or maybe future collaborators would like to provide detailed instructions for placing the PCB orders, create 3D printable enclosures for the PCBs so they're not just mostly loose. We'd like to improve the refresh rate of the GUI with some software optimizations. Right now it only runs at about 2 samples per second on my PC at least. I'd like to provide some more documentation for extending the microcontroller software to other hardware options. Right now, the number of axes and the number of sensors is hard-coded, although it doesn't take a very complicated change to implement it for other numbers of nodes. And I'd like to help users at other universities or other institutions use our design to get their testing done faster. So I look forward to hearing from anybody who's interested in implementing their own Helmholtz cage, and thanks for checking out my poster presentation at the CubeSat Developers Workshop, and I look forward from hearing from you. Thanks.